Welcome to another tutorial of the thermal system design class. In these tutorials, we're gonna solve for a turbulent flow over a heated cylinder. So from last time, we solved for laminar flow, and we have similar conditions. Our working fluid is air. The cylinder diameter is 2 inches. The cylinder wall temperature is 80 degrees Celsius. Now our inlet velocity is dependent on the Reynolds number, and it's gonna be 10,000. So from last time we had a 100 Reynolds number, so now we're accounting for turbulent flow. Our inlet temperature is 25 degrees Celsius, just regular atmospheric temperature. And we're solving for the contours, the velocity, temperature, pressure, and the plots are going to be velocity, temperature, and pressure at different distances from the center of the domain. So I'm taking the same problem that we did last time, same geometry mesh. So you can recreate it yourself. It's gonna be the same geometry. It's gonna be the same geometry, and you can recreate it yourself. Or I'm using the same problem, and what I'm gonna do is that I'm gonna connect the previous geometry that we used to our new one. As we can see, we can just drag another fluent analysis, and it's gonna allow us to drag select meshing and connect it to our mesh. And if we open it, if we open setup, it's gonna ask us if this is a 3D problem, which is it is. We're gonna select double precision, and when we start it, we can see that we have a similar geometry and meshing than we did on last problem, which was the laminar flow over the heated cylinder. So we'll go to general, we'll check if our meshing is good, and it's checked and doesn't give us any error. We can even report our quality and see our different zones, the inverse orthogonal quality of the meshing. We can go to display, we can display the edges instead of the faces, or whichever you rather have. So now if we go to model, we're gonna turn on the energy model, and if we go to viscous from last time, we just selected laminar flow. In this case, we have several options to simulate turbulent flow. We have the K epsilon, K omega, we have large edgy simulations, detached edgy simulation. One of the most basic and common ones that you're gonna use is the K epsilon, but feel free to navigate through the other models just so you can get familiar with it. So if we go to the K epsilon model, we can see that there's 3 different types of model. Is the standard, the RNG, and the realizable. So depending on the problem that you have, and if you're asked a specific question, you're gonna use these 2 other models. But if you're not, which in this case we're just trying to solve for a simple turbulent flow, we can just use a standard K epsilon model. And we also have here on the bottom of the K epsilon model a near wall treatment. So near wall treatment is basically how your model is going to treat the boundary conditions on the domain. So we have a standard wall function, we can do a scalable non-equilibrium wall function, and we have different options. In our case, we're just gonna go for the standard wall function. We have more options like viscous heating, and here one of the most important things is the model constants. So we have the model constants for this specific correlation, for the K epsilon, and these material constants are the optimal ones gotten from literature. You can change these values, but if you don't know the actual values, or if you have not done the calculations yourself, I would recommend just to leave it as the default, as this will give you the default model. One of the good things of ANSYS and one of the reasons why we use it is because the built-in models already give us good solutions, and just specific situations are gonna ask us to change these type of material constants or model constants. You also have here the user-defined functions. In this case, we have none. We'll just click OK. So we can see that it changed now. So now for models, we'll go to materials. We can see our material is just simple air. We can see the properties of air. Close it. We can see our cell zone conditions. And if we go to our boundary conditions, this is where we'll have to change some things. So if we go to the inlet, we'll select velocity inlet again. It's going to open this window. So the velocity magnitude that we're going to use, same as last time, we're going to take our Reynolds number, which in this case is going to be 10,000, our viscosity, our density, our diameter, and we're going to plot it into the Reynolds equation, and we're going to isolate for velocity. And the actual velocity that we obtain from right now is going to be 2.874 meters per second. 74. And now we can see that we have a new option at the bottom of the velocity magnitude, which is the turbulence. So from last time, if you go back and if you change your model to if you change your model again to laminar, for example, let's click OK. And if we go back to our boundary conditions, we can see that the option disappeared. So this option is gonna be the one that is gonna allow us to run the turbulence flow over the cylinder. So if we go to specification of method, we have different options. We have the K epsilon, we have the intensity and length scale. In this case, we're gonna use intensity and hydraulic diameter. So it's going to ask us for our diameter and our turbulence and turbulent intensity. You can actually learn this from different mathematical equations. In this case, we're not gonna cover the turbulent intensity. We're just gonna use the default, which is 5%. And our hydraulic diameter is just gonna be the diameter of the cylinder. Let's change this to change the units for this. Let's look for length. Change it to inches. We'll say that this is 2 inches. We'll go to thermal. Our thermal conditions on the inlet are the atmospheric, which is just 298 kelvins. We apply it and we can close it. We go again to boundary conditions. Let's go to outlet. We'll change this to outlet flow. The flow rate weight, let's just leave it as 1. The cylinder wall is one of the things that we have to change. We'll go to cylinder wall, edit. Momentum, we're gonna leave it as it is. But our thermal will go to temperature. The temperature at the cylinder wall is gonna be 353 kelvins. So we change that number, apply it, we close it. Inlet, we change that. The symmetry wall, there's nothing to change. Even if you click it, there's no option. And if we go to reference numbers, we can see, for example, in the inlet, the different values that we assign our problem to be. We can see our velocity, our temperature, just to double check that everything is the way that it's supposed to be. Now if we go to solution, We go to methods. We're gonna keep on the standard and conventional form of to solve this problem. So we'll go to simple. We'll leave this as least square cell base. The pressure, let's just leave it at standard. We don't need pressure on this problem too much. Our momentum, let's leave it as second order upwind. Our turbulent kinetic energy, second order, and as well as the turbulent dissipation rate, second order. That is going to give us a more precise solution. Now if we go to controls, we can see the different values. We can see new values here, the turbulent kinetic, turbulent dissipation rate. We'll leave this as a default. And if we go to monitors and residuals, let's change our convergence criteria for the continuity, the x velocity, the y velocity, and the c velocity. And then if we click on initialization, we'll go to hybrid. We can initialize. We can see that in our text console that the values for the initialization has been performed. Then we go to run calculations. And let's run 120 iterations. First we check our case. Consider realizable K epsilon. Okay, we're not gonna need this. No, close. And we can start calculating. So it's gonna start creating the residuals until it reaches our number of iterations. As you can see, it's gonna take you a little bit more time from last time. The problem is gonna be, it's more complicated. I'm running less iterations for the moment just so we don't waste so much computer timing. And we can see how our continuity goes, our epsilon, our x, y, and z velocities are right here in these three lines. You can see our energy, our k epsilon, and our k and our epsilon are right here. So now that our calculations have finished, we can start post-processing our results. We're gonna do that on the next tutorial. But we can see that the residuals, how they look.